All right, so now we're going to dive into some details of photoelectron spectra and interpret some spectra. So we first have to talk about what gives rise to various peak shapes in these sorts of spectra. And we talked very briefly about the vibrational fine structure in the spectra in the last video. And it turns out only bonding or anti-bonding molecular orbitals will give rise to vibrational structure. So if you're exciting a electron out of, you're ejecting electron out of a bonding or an anti-bonding MO, you will have vibrational structure, okay? Where does this vibrational structure come from? Well, it comes from the molecule upon ionization. Remember, you're removing an electron. So another way of saying that is you're ionizing, right? We said ionization potential. So you're ionizing it. And when you do that, you have removed an electron, and the molecule can now go to an excited vibrational state in some cases. That's where the vibrational fine structure comes from. How do you access those vibrational states? You access it through a bend or stretch, right? I mean, that's what a vibration is. We know that from vibrational spectroscopy. Fundamentally, all there are bends and stretches. So here, right, when you ionize, you're going to have a change in bond order if you're ionizing from a bonding or an anti-bonding MO, okay? Your bond is going to contract or extend. And because of that, that's going to naturally be doing a stretch, right? So naturally, you're going to go to a vibrationally excited state. So that's how they're accessed. If you think about this, you're going to get a smaller spacing in the vibrational fine spectra of PES peak than you would expect for a neutral molecule when you're ejecting an electron from a bonding MO. Why? If you eject one electron from a bonding MO, that's going to decrease your bond order by 1/2, right? 2 electrons per bond. Remember your MO counting rules. So if you decrease your bond order by half, you've gone from a double bond to a 1.5 bond, your bond strength, K, remember in this expression that gives you your fine structure frequency, nu, K is going to decrease, okay? So if K decreases, nu decreases, you're going to have smaller spacing when ionizing from a bonding MO. The exact opposite is true when you ionize from an anti-bonding MO. You're going to have a larger spacing. Why? If you remove one anti-bonding electron, that's going to increase your bond order by 1/2. So if you start with a double bond, you're going to end up with a 2.5 bond upon ionization. That's going to increase K. That's going to therefore increase nu, which is your vibrational fine structure spacing. So that's where this vibrational fine structure spacing comes from. It follows as a corollary that non-bonding MOs have little to no vibrational structure. And why is that? Because if you eject an electron from a non-bonding MO, you're not changing the bond order. And if you're not changing the bond order, you're not expanding or contracting. In other words, you're not stretching. That means you're not accessing these vibrational states, right, that are associated with stretches. However, okay, multiply degenerate orbitals, this is now another rule kind of on top of it. Multiply degenerate orbitals split a peak into a multiplet, even in the absence of vibrational structure. So even if you're non-bonding MO, you can still have a split in your peak. It's not going to be a vibrational structure. It's going to be another type of splitting, okay? And this type of splitting can occur whether you're bonding, anti-bonding, or non-bonding. This can occur for 2 reasons. One is something called spin-orbit coupling. Maybe you've gone over this in your PChem class, but spin-orbit coupling, very qualitatively, is this idea that the spin of a neighboring electron can change the orbital energy. It actually splits it. Basically, the electrons in neighboring orbitals, okay, are interacting with one another. It has to do with electron-electron repulsion, okay? And this can cause doublets. Okay, so it's like, you have a px and a py, electron in each of those can do spin-orbit coupling. This effect turns out to make a doublet for doubly degenerate orbitals and a triplet for triply degenerate orbitals. And spin orbit coupling is a bigger effect for heavier atoms. Why is it a bigger effect for heavier atoms? Heavier atoms have larger atomic orbitals, right? They're lower on the periodic table. They have larger atomic orbitals. The atomic orbitals are bigger, so they tend to like interact with one another more. So that's the idea. Spin orbit coupling, bigger effect for heavier atoms. It will cause doublet for doubly degenerate, triplet for triply degenerate. We'll see examples of this. Jahn-Teller effect is another thing that can cause multiply degenerate orbitals to split. Okay, so even if you don't have spin orbit coupling playing, remember the Jahn-Teller effect. We talked about this. This was the idea that molecules will want to distort from their idealized symmetry if there's electronic degeneracy, right? And now you've made an ion. Well, the ion structure that's the most in PES, you've made an ion, right? The ion structure that's the most stable might not be the structure of the neutral form before you shined light at it. And so you might have Jahn-Teller distortion in order to get to a more stable state, okay? So you're going to a lower symmetry state, just like what we saw with the octahedral complexes a lot of times ended up being D4H, Jahn-Teller effect, okay? This effect is a bigger effect for lighter atoms. Why is that? Because bonding of lighter atoms is usually stronger, okay? So then if you split from that bonding with Jahn-Teller, right, then you have a bigger effect. So basically, you don't have to worry too much about these two effects, just knowing that they're both there. They have opposite trends in terms of which one operates with which in terms of heavier atoms or lighter atoms, but they both cause splitting in peaks, okay? All right, so now we can look at the photoelectron spectrum of methane as an example. We went over the molecular orbital diagram of methane. Okay, we didn't really derive it, but I showed it to you. And here it is. I'm going to show it to you again. What you can see is that there are 4 molecular orbitals. Okay, 2 of these are occupied. The other ones, these anti-bonding ones, are not occupied. There's 2, 4, 6, 8 electrons, valence electrons. Why is there 8 valence electrons? Well, 2 electrons per bond. That means you have 4 bonds, right? 4 single bonds. That's what you expect from methane. 4 CH bonds. Cool, so that all checks out. Now that you have 8 electrons, okay, you can use PES to probe the energy of these electrons, right? And what would you predict? You predict that you have 2 different energy levels. And that's exactly what you see in the photoelectron spectrum. And what's even more pronounced is that you see, for one, the peaks are in a 3-to-1 ratio. Why would they be in a 3-to-1 ratio? Because you have 6 electrons in the T2 and 2 electrons in the A1. So a 6-to-2 ratio is a 3-to-1 ratio. So it's just like NMR spectroscopy, where if you have more protons, right, there'll be an integral associated with that, right? You'll have a bigger peak. Same thing with PES spectrum. You have 6 electrons here, 2 electrons here, so you have a 6-to-2 or a 3-to-1 ratio. And the ordering of the energies is correct. And we actually get out the energy from this. This is very powerful, right? So you can see the A1 has a higher ionization potential than the T2. That's what we predicted based on our MO, because our MO had the A1 lower in energy. So it takes more energy to eject an electron from this lower A1. Why was this A1 lower in energy than the T2 in terms of constructing the MO diagram, de novo? Because the 2s orbital is more stable than the 2p, right? And so you'd expect that we can look up the ionization energy of a 2s orbital for carbon, right? It's 19.5 electron volts. And so since this is a bonding MO, your A1 better be greater in energy than, or more negative in energy is another way of saying it, than 19.5. Indeed it is. The 0-0 transition is around 23, right? And for T2, it's around, I don't know, 13.5, okay? Again, that's lower than 10.7. That's lower than the energy of the 2p orbitals on carbon, the ionization energy of the 2p orbitals on carbon, because this is bonding orbital. So everything's matching up. It's really powerful because we get these actual energies out of it. And this, everybody, is the hardcore evidence of why hybrid orbital theory is incorrect, because you have 2 different energies. You have 2 different energies in methane, not 4 equivalent sp3 orbitals. Instead, you still have 4 equivalent bonds, same bond length, same CH bond length, but each of those bonds has 3/4 T2 character and 1/4 A1 character. Bonding is more delocalized than Lewis structures and hybrid orbital theory tell us. The actual truth is that bonding looks something like this MO diagram. Okay? Very important. We can make some predictions about, maybe we'll take a break there and we'll go to the next video. Okay.